Welcome students to this session on operations research. In this session we will be discussing about Big M method, which is a type of artificial variables technique. Big M method is used whenever the constraints of an LPP model are of greater than or equal to type. At least if at least one constraint in the LPP is of say greater than or equal to, that is LHS is greater than or equal to RHS or LHS equal to RHS type, we need to add artificial variable to the left hand side of the constraint to get the initial basic feasible solution, so that we can continue the iterations with the simplex method that we have discussed and seen in our previous sessions. So in simplex method, all the constraints were of LHS less than or equal to RHS, LHS less than or equal to RHS. So in simplex method, when LHS was less than or equal to RHS, you added slack variables to the LHS to balance it and to bring it to equality, that is LHS. To bring LHS equal to RHS, you introduced slack variables, so that when you introduce slack variables to the left hand side of the constraint, LHS becomes equal to RHS. Whereas in some cases, when the LHS is having a sign, inequality sign greater than or equal to that of RHS, that is when LHS is greater than or equal to RHS or LHS is equal to RHS, then we cannot add slack variables. So one of the techniques used to solve such problems is the Big M method. So in this session we will be discussing about a maximization case which involves Big M method. So the Big M method, as you can see on the screen here, following steps have to be followed. The steps to be followed in Big M method are: first, express the problem in the standard form, then add non-negative artificial variables to the left hand side of the equations corresponding to the constraints of the type greater than or equal to. Then we assign a very large penalty, minus m for maximization and positive m for minimization, in the objective function. So we will add a very large penalty, that's why it's called a penalty method also. It is also called as one of the artificial variable techniques, Big M method or the penalty method, where you are introducing now a very huge, very large penalty, which we say assume as m, capital M, and we will say for a maximization problem the coefficient of m will be -1, whereas for a minimization problem the coefficient of m will be +1. So in the objective function, when we show this m in the when we represent this m in the maximization problem, the coefficient of m will be -1 for maximization problem, and for minimization problem the coefficient of m will be +1. Now solve the modified LPP by simplex method until any one of these cases may arise. Now from here on, from this particular third step onwards, once you have introduced the artificial variables and say the surplus variables, here we are not using slack variables. Slack variables will be used only when LHS is less than or equal to RHS. When LHS is less than or equal to RHS, then we can use slack variables. But in standard forms where you have LHS greater than or equal to RHS or LHS equal to RHS, then we have to use, say, surplus variables and artificial variables in the case of greater than or equal to sign, and only artificial variables in the case of equal to signs. So here there are three cases that might arise. The first case is if no artificial variable appears in the basis and the optimality conditions are satisfied, then the current solution is an optimal basic feasible solution. So if no artificial variable appears in the basis and the optimality conditions are satisfied, then the current solution is an optimal basic feasible solution. So whenever in the end, this is, we are now talking about the end. When can you say that a particular problem has reached the optimality? So if you get an optimal condition, the optimal conditions remain the same here. For a maximization problem, when Cj minus Zj values, all Cj minus Zj values, when all Cj minus Zj values are less than or equal to 0, for a maximization problem, we say optimality is reached. Similarly, for a minimization problem, whenever all Cj minus Zj values are greater than or equal to 0, then we say optimality is reached for a minimization problem. So always this rule will remain same. For every maximization problem, all Cj minus Zj values should be less than or equal to 0. For all minimization problems, Cj minus Zj value should be greater than or equal to 0 for the optimality condition to be reached. So that remains same here. So if in the end, in the solution, if no artificial variable appears, if there are no artificial variable appearing in the basic solution or in the basis, and the Cj minus Zj or the optimality conditions are satisfied, then the current solution is an optimal basic feasible solution. Clear cut solution. It's the optimal basic feasible solution. The second case is if at least one artificial variable appears at the basis with the value of 0 at 0 level, and Cj minus Zj or the optimality condition is satisfied, then the current solution is an optimal basic feasible solution, but it is degenerate. That is, it's a degenerate basic feasible solution, optimal basic feasible solution. The condition is at least one artificial variable which you have introduced should appear in the basis with a value of 0 at 0 level, and all the optimality conditions have to be satisfied, and the current solution should form a, and then we say that the current solution is an optimal basic feasible solution but degenerated, but it's a degenerated solution. Similarly, the third condition, if at least one artificial variable appears in the basis at a positive level with a positive value, at least one artificial variable appears in the basis or the basic solution at a positive level, and the optimality condition is satisfied, then the original problem has no feasible solution. There is no feasible solution put to the problem, which means the solution satisfies the constraints but does not optimize the objective functions. The solution that you have got will satisfy all the constraints given but will not optimize the objective function, since it contains a very large penalty m. So it is called as a pseudo-optimal solution. It's called as a pseudo-optimal solution. Please note, while applying simplex method, whenever an artificial variable happens to leave the basis, we will drop that artificial variable and leave out all the entries corresponding to its column from the simplex table. We will drop the artificial variable and omit all the entries corresponding to its column from the simplex table. So this is the underlying principle. The knowledge or the understanding of these conditions are required before you solve the big M method, because these all talk about the interpretation of the results, of the solution. So you can see here there are three specific cases here discussed. So you have to now, once you arrive at the Cj minus Zj values, that is the optimality conditions, when you make a particular claim or when you conclude, when you say that this particular problem has a solution, you have to check whether it has a clear solution, Is it a degenerate solution or is it a pseudo optimal solution? Let us take a problem now. Solve the LPP using big M method. So here an LPP is given to you with an objective function maximize z is equal to 3x1 plus 2x2. There are two decision variables x1 and x2. Objective function is to maximize this. Maximize z is equal to 3x1 plus 2x2. Subject to the constraints 2x1 plus x2 less than or equal to 2. So this is similar to the first constraint is similar to the constraint that you have seen in the simplex methods earlier. So 2x1 plus x2 less than or equal to 2. But the second constraint is 3x1 plus 4x2 greater than or equal to 12. So in the first constraint, LHS is less than RHS, less than or equal to RHS. In the second constraint, LHS is greater than or equal to RHS. Okay. So what you have to do now, introduce a slack variable. Whenever the constraint is less than or equal to, you add slack variables like you have done in your simplex method. So in the first constraint, you will add slack variable S1 and bring in the equality sign. We can see here 2x1 plus 1x2 plus 1s1 is equal to 2. So this s1 here with the coefficient of plus 1 is the slack variable. But in the second constraint 3x1 plus 4x2, the sign is greater than or equal to. So simplex method, say the general format of a simplex model cannot be, is not represented here. So greater than or equal to sign is there. So LHS is greater than or equal to RHS. So here you cannot add a slack variable. You have to introduce a surplus variable S2. So you are now adding a surplus variable S2, but the surplus variable will have a coefficient of minus 1. You are deducting something from this LHS because LHS is greater than or equal to RHS here. You are deducting something. So the surplus that is there you are deducting. So minus 1 S2. So 3x1 plus 4x2 minus 1 S2. And whenever you deduct or introduce a surplus variable, an artificial variable has to follow. You are also adding an artificial variable to that. So always remember, whenever there is a greater than or equal to sign in the constraint, you will first introduce a surplus variable with a coefficient of minus 1 and an artificial variable with the coefficient of 1. Since this is the first artificial variable that is coming in the entire LPP, you are representing it by A1. There is only one artificial variable. Artificial variable will not come whenever the sign is less than or equal to. Artificial variable and a surplus variable will come when there is a greater than or equal to sign. So first constraint is represented as this constraint 2x1 plus x2 less than or equal to 2 is represented as 2x1 plus 1x2 plus 1s1 is equal to 2. Similarly 3x1 plus 4x2 greater than or equal to 12 is written as 3x1 plus 4x2 minus 1s2 plus a1 is equal to 12. S1 is the slack variable with the coefficient 1, S2 is a surplus variable with the coefficient minus 1, and A1 is an artificial variable with the coefficient of 1. Now what about the objective function? As you have seen in a previous simplex calculations, the slack and the surplus variables will have a coefficient of 0 in the objective function. So 3x1 plus 2x1 maximization z is equal to 3x1 plus 2x2 plus 0s1 plus 0s2. And as we have already seen, this a artificial variable which had a coefficient of 1 in the constraint will have a coefficient of m in the objective function. M is a very big number, huge number. M is a very big number which is introduced in the objective function as a coefficient of artificial variable. If it is a maximization problem, the coefficient will be minus m or minus 1 of m. M will have a coefficient of minus 1. If it is a minimization problem, m will be plus. The coefficient of m will be positive, plus 1. So in this case, since it's a maximization problem, the objective function will be maximize z is equal to 3x1 plus 2x2 plus 0s1 plus 0s2 minus m a1. So let us see how the simplex table looks now. So here there are 1, 2, 3, 4, 5. You can see 5 variables here, 5 variables, and there are 2 constraints. 5 variables and 2 constraints are there. 2 constraints are there. So you can see here Cj is the coefficient of the objective function. This is the Cj is the coefficient of the objective function. Your objective function was 3x1 plus 2x2 plus 0s1 plus 0s2 minus ma1. 3x1 plus 2x2 plus 0s1 plus 0s2 minus ma1. And in the basis you can see you now introduce the slack variable s1 and the artificial variable a1 here. Slack variable s1 and artificial variable a1 will come into the basis, and the coefficients of s1 will be 0 and coefficient of a1 will be minus m because it's a maximization problem. And these are the coefficients of the constraints. First constraint was 2x1 plus 1x2 plus 1s1 plus 0s2 plus 0a1 is equal to 2. Second constraint was 3x1 plus 4x2 plus 0s1 minus s2 minus 1s2 plus 1a1 is equal to 12. And the zj values you can calculate 2 into 0 plus 3 into minus m, that is minus 3m. Similarly 1 into 0 plus 4 into minus m, and so on. So this is how you calculate the zj values. For example, if I take this value, 1 into 0 is 0 plus 0 into minus m is 0. Similarly here 0 into 0 plus minus 1 into minus m, that is m plus m plus m. Similarly here 0 into 0 plus 1 into minus m is minus m. This is how you calculate this particular zj values, and this one you can ignore in the first stage. This thing need not write here, because this is the initial stage, no need of writing it here. In the end final solution you can write the zj value of the solution. Now if you see here Cj minus Zj values, so this will be 3 minus 3m, that is 3m plus 3, 2 minus 4m, 4m plus 2, 0 minus 0, 0 minus m, so this should be minus m, make a small correction here, it is minus m, and minus m minus m is 0. You can see here Cj minus Zj values. When you look at this Cj minus Zj values here, you observe here, this Cj minus Zj values here. This is a maximization problem. So optimality is reached only when Cj minus Zj values in a maximization problem. Optimality is reached when Cj minus Zj value is less than or equal to 0. Since m is a very large number here, you can very well imagine these two values are positive. M is a very large number. These two values are positive, and out of this 4m plus 2 is the maximum one. 4m plus 2 will be the maximum, the highest value. So this will now become your key column here. Because optimality is not reached. Cj minus Zj values, all Cj minus Zj values are not less than or equal to 0. They are greater than or equal to 0. Under x1 and x2 decision variables, you can see the values of 3m plus 3 and 4m plus 2. 4m plus 2 is the highest positive value. So that column corresponding to 4m plus 2, that is a column containing x2, now becomes the key column. And now find the ratio here. So now x2 will come in x2 now becomes your entering variable. Now when I take the ratio 2 divided by the element in the key column, so 2 by 1 will be 2. This one, 2 divided by 1 is 2. Similarly, 12 divided by 4. 12 divided by 4 will be 3. So as you have done previously, the minimum ratio row here, which is the minimum ratio row? The minimum ratio row is this. The minimum ratio row is this. So S1 will now become the leaving variable because it corresponds to the key column. S1 will be the leaving variable now because it corresponds to the key column. You can see here the same table is shown here. Same table. So this should be minus m here. This is minus m. So you can see here all Cj minus Zj values again, but before that you have to know this solution is not optimal now, because you already seen since all Cj minus Zj values are not less than or equal to 0, the solution is not optimal. That is why what you have done, you have selected the key column, you have seen key column you have selected here, and based on the ratios you have seen the key row, and this now becomes your key element. This is your key element or the pivot element, the key element or the pivot element now. So now x2 will be the entering variable or the incoming variable, and s1 will be the leaving variable. S1 will be the leaving variable. So the column containing x2, so the column containing x2 is the key column, and the row containing s1 will be the key row. Similarly, the leaving variable is s1 and the entering variable is x2. The intersection element of the key row and the key column is called the key element. You all know that. So in this case, the key element is 1. Now convert this element into 1 by dividing each element in the key row by 1 and the remaining elements in that key column as 0 using the formula new element is equal to old element minus the product of the key row element and the key column element divided by the key element. So you have to do the calculations now. So since the first row was the key row, the calculations there are very simple. Divide every element in the key row by the pivot element. In this case, the pivot element is 1. So divide by 1 each of the values in the key row by 1 and the pivot element by itself. So you get a value of 1 there. But in row 2 calculations, again you have to go by the same formula. New element is equal to old element minus product of the key row element and the key column element divided by the key element. So the row 2 calculations will be 3 minus 2 into 4 divided by 1, which is equal to minus 5. So the first value in the row 2 will be minus 5, 0, minus 4, minus 1, 1 and 4 respectively. See, now everything is similar to what you have done in simplex method. Those who have not been introduced to simplex can refer to my previous videos. There are two separate videos, two different problems of simplex method has been discussed. You can go there and just understand how this calculations of the new element is done. So after the first iteration, we can see here, after the first iteration here, x2 has come inside. X2 comes in the basis with a coefficient of 2. And you can see these are the values. And similarly, by the calculations that you have done previously, these are the new values, new elements of the second row. These rows we have already seen. Old elements divided by the key element. You get this. Whereas here, that formula which we have discussed in the previous slide, that has to be utilized here. And then again you find out the Zj values. The only change here is instead of the slack variable s1, x2 has now entered and s1 has left the solution. X2 will come with a coefficient of 2 because that is the coefficient of x2 in the objective function. So again calculate now the Zj values. So 2 into 2 is 4 plus minus 5 into minus m. So it will be 5m plus 4. 2 into 1 plus 0, 2. Again 2 plus minus 4 into minus m, that is 4m plus 2, 0 plus m, that is m, 0 minus m, that is minus m, 2 2s are 4, 4 plus minus 4m, 4 minus 4m. So these are your zj values. Find out the cj minus zj values. These are the cj values. 3 minus 5m plus 4, 3 minus 5m plus 4, so that will be minus 5m minus 1, minus 5m minus 1. Similarly here 2 minus 2 is 0, 0 minus 4m plus 2 is minus 4m minus 2, 0 minus m is minus m, minus m minus minus m is 0. So all cj minus zj values here, if you look at this, are less than or equal to 0. All these values are less than or equal to either negative or 0, because m is a very high value. M is a very high value. So minus 5m minus 1, minus 4m minus 2 are very high negative values. So all these cj minus zj values here will be less than or equal to 0. So optimality condition is reached. Optimality condition is reached. But remember the three conditions which we specified initially. The first condition was all cj minus zj values less than or equal to or rather depending upon maximization or minimization, the optimality conditions have to be satisfied. Okay, this is a maximization case, so cj minus zj value should be less than or equal to 0. That is true here. If an artificial variable does not appear in the solution and this cj minus zj value is satisfied, then we say the problem has a optimal solution, basic optimal solution. But in this case, you have reached the optimality condition, but an artificial variable still remains in the solution. An artificial variable still remains in the solution. An artificial variable is still remaining in the solution here. So this is condition 3. Now artificial variable is remaining in the basis with a value, with a solution of 4, it's a positive value. Artificial variable is there in the final solution when optimality condition is reached with a positive value. So we say this solution, this particular problem, even though the optimality conditions are satisfied, this LPP does not possess any feasible solution, but it will possess a pseudo optimal solution. The third condition, the first condition was optimality condition should be satisfied, no artificial variable should be there in the solution, but here there is an artificial solution. So first, it is not first condition. We will not interpret it as the first type of condition. First condition is not satisfied. Second condition was artificial variable can be present, at least one artificial variable can be present, or one artificial variable can be present with a value of 0. Then solution is there, but it is degenerate. If artificial variable is present with a value of 0, but here artificial variable is present but the value is not 0, it is a positive value, then it becomes a third condition, that is pseudo optimal solution. The LPP possesses a pseudo optimal solution, which means the constraints are satisfied, but the objective function is not satisfied. It does not conform to the constraints are, it conforms to the constraints. Constraints are satisfied, but the objective function, no. So this is the solution to this problem. This particular problem, optimality is reached, but the solution is a pseudo optimal solution. So in the next session, we will again take up a minimization problem and apply big M method and see how you get some more insights into the big M method. Thank you.